How you doing? So we did a Fourier transform, and now I'm going to show you a little something different. Um, and this might be from some live data. So here's a Shure SM57 microphone. I just copied this off the web, and you can see that it has a frequency response that's kind of flat here from 200 to see, this is 1,000, 2,000, 3,000 hertz or so right here. Okay, so this is a logarithmic scale. Just in case you don't recognize how to read this, this is a 1 kilohertz. This is 2 kilohertz, 3, 4, 5, 6, 7, 8, 9, and finally here is 10 kilohertz, right? So, in this space, you go from 1,000 to 10,000, a factor of 10, which is the same space as you would go from here. Although I think this might be a little more expanded. So anyway, oh, actually, it's from here to here is a factor of 10, and from here to here is a factor of 10. So this is a bodeplot. It has frequency on the x-axis, and it has a relative response in dB on the horizontal axis, or on the vertical axis. And so this response in dB, a dB is a logarithmic unit as well. So this is really a log-log plot, although the log is already taken in this one. So if I just kind of look at what's all in this plot, see the response rolls off below 100 hertz, rolls off above 10K. It's pretty flat in this area, a little bit more sensitive in this area. So that's a lot of information in one single plot. So so bodeplot is named after H.W. Bode, and as I said, the x-axis is in frequency. In this case, it's hertz. You could also do it in radian frequency, but radian frequency doesn't mean quite as much to me as hertz does. The y-axis is in dB, and that's named after Alexander Graham Bell. And a dB is a tenth of a bell, or a decibel, and so hence that's how you get the name dB. Again, the x-axis is logarithmic, and the y-axis is linear, but a dB is a log unit. So here's what a dB is, and you can see it's got the log 10 in there. So what is a dB? That's a good question to ask. Well, so a dB is the ratio of two powers. So here's power out, power in. You take the log 10 of it and you multiply it by 10. Right, so if you didn't multiply by the 10, you'd have a bell, but we use decibels. And so here's a network. You have power in, you have power out, and a dB is always a power ratio. I mean, this is really the only formula for a dB. Now, you might have, say, a 50 ohm input here and a 50 ohm output here, and you might have voltage measurements. And if that were the case, then you could use P is equal to V squared over R to compute the power. And so you could put the power, you could substitute in there, so you'd have V out squared over R over V in squared over R. The R's will cancel out, and you have V out squared over N, V in squared, and that quantity is squared. Well, if you take the log of x squared, you get 2 times the log of x, right? And so the 2 comes out here, and now that becomes 20 log 10 of V out over V in. And so there's the decibel in voltage form. But remember, a decibel is always a power measurement. So this is what this looks like. So you have a network with P in, P out. This is the formula you use. You have a network with V in and V out. And here's the network that you use. You could also do the same thing if you had two currents. Now you can also I'll go back here for a minute. These are relative measurements, right? So this measurement, if I say I have 15 dB, that means that there's a gain of 15 dB for the output voltage over the input voltage. It's relative. The gain is relative to this. But I can also do some absolute units, and to do that, I just in the P in, I just have 1 watt. So P out divided by 1 watt, take the log, multiply by 10 of it, and so I have, so 20 dBW is 100 watts, right? So if I put 100 watts in here over 1 watt, that's 2 to the power 10. I take the log of that, that's a 2. This piece would be a 2, and I would get 20 dB. If I if I were to say put 1 watt out here with 1 milliwatt in, then that would be a ratio of 1,000. The log of 10 of 1,000 is 3, and so I'd get 30 dBW. So 1 watt is 30 dB MW. And so you can generate Bode plots. So you can generate them from measurements, which is the way that Shure microphone plot was made. You can do it by using equations, which we're going to do in the homework. And you do it by the asymptotic method, and that's I'm going to leave that to somebody else to explain that to you. But basically, if this is the transfer function, so this is V out over V in, and you have the units over here, so it's V over V, so it's it's unitless. I might go back here for just a second and say, if you take the log 10 of some unit, say feet, I don't know what log 10 of feet are, but that's a really odd unit. And but if it's volts over volts, it's unitless. You take the log of it, then it'll all work out okay. Anyway, so let's go back to here. So here's going to be your homework problem. And while I'm not going to cover the asymptotic method, I will say that S is j omega, so it's j times the frequency, and we're going to span a bunch of different frequencies. This one's going to have a breakpoint at 5, and so if I were looking at the asymptotic plot, I would draw a curve up. This one's going to break at 10, and it's going to break down, and this one's going to break at 100, but it's squared, so it's going to break at a steeper rate. So I'm not going to go over that too much, but I did want to introduce you to what a Bode plot was, and then in your homework you'll get to actually do one.